Hi, I am Eli T. Brown. The T is useful if you're looking for me on Google. And I am from DePaul University. So I'm going to talk today about some work trying to build a framework for discussing these these machine learning and human interaction works that we've all been doing over the years. So I think this will be an easy crowd for the motivating assertion, which is that human and machine together are greater than either of them alone. I don't think I have to argue about that here, but I do want to provide a motivating example because I find actually it can be difficult to think of one where there's a big victory for man and machine over either machine or person. And this one comes from chess. So in 1985, Garry Kasparov, famous chess player, grandmaster, beat 32 computers at a time. Could lay out 32 of the best machines, and he could walk around, play one move, go to the next, play another move, and he just destroyed all of them. But by 1996, IBM had built Deep Blue, a big, powerful, special chess machine, and while he beat it in 96, the rematch in 97 didn't go so well, and he lost. And there were enormous headlines, computer beats man, we're falling to the robots, whatever. But Kasparov was not completely deterred by that. I mean, he said that by 2004, computers had become too strong to even bother with human matchups. There was just no way a human could beat one. And by today, a laptop can crush any grandmaster. But rather than just cede to the machines, he thought the pairing of the two together could be really interesting, and he created what he called advanced chess, which is his way of seeking the highest level of chess ever played. Take a person and give them the ability to reference a machine while they play. And so you won't have people making the occasional stupid mistake. You won't have people struggling to remember the different end games and start games that normally grandmasters think of from the literature as these games unfold. And so in 1998, there was a match between he and another grandmaster, and they actually went to a draw, even though I'm sure he thinks he should have won. But it evolved to freestyle chess, which is the most interesting conclusion of this. Because he said, so that's two grandmasters, each with a beefy computer. What if we just open it up and say, we're going to play chess, you can use whatever computers you want, you can compete whomever you want. And so we had a competition where there were grandmasters, there were massive computers like Hydra, which could beat really any person. And then there were teams of people with laptops. And the people who won were actually two amateur chess players using 3 laptops at the same time. So the winning overall strategy, the best chess that could be played at that time, was strategically integrating machine and human. So that being the motivating example, the particular motivation for this framework is that I think we've seen lots of different examples of machine learning and human coming together in different types of technologies. There's a whole bunch being talked about today, which are fantastic. But it seems to me that it's covered across many different fields, and we need to bring together the examples that exist, categorize them to understand how they fit together, and use that to see what can come next, what's missing, and what are the challenges to the different communities that make up this interactive machine learning community. So here is one, and I hope it sort of can be some sort of example to kind of be a roadmap to people coming into this field wanting to do work in this. Let's see if the mouse pointer, maybe I'll just walk through without that. So basically, the idea is, first of all, there's a giant loop is the main structure here. So we have the person over here, they're interacting through some interface with a machine learner in the back end, and then this creates some model which updates the interface. And so there's some feedback loop happening here. And categorize the different types of interaction, which I think is kind of the most interesting part of this, especially for this crowd, which breaks down into incidental. So that would be interactions you just sort of casually do without thinking about it, moving the mouse, clicking at the keyboard, whatever. Exploratory interactions are those that involve interacting with the interface in an exploratory way as opposed to in a way that's intended to update a model. We have parameter tuning, which are interactions that are specifically and directly intended to update the model by changing its parameters. Explicit model steering, which can be direct manipulation of the data, but with the intent to build some model or improve some model. And then implicit or indirect model steering, where you're doing some interaction that you want to do anyway, and this improves the model. And so I will go over some examples to help clarify all these. I'm not going to review the different types of machine learning. I think people will know those here, but they are in the quick discussion is in the paper, and if you want that to guide towards different literature, that gets there. So one really classic example, human and machine, spam filters. We all use these in our email. This is an example of implicit indirect model steering. So you're interacting with your email, and you want to get rid of emails that annoy you, and you tell it because you want them gone, but actually at the same time it is improving your spam filter. So the data goes from those interactions to a supervised algorithm generally and improves a data model that can then have an impact on your interface. Another example is IPCA. So this is an interactive form of PCA. It's a high-dimensional data projection, but in this interactive form, you get to tweak the parameters yourself, decide the importance of the various input dimensions, and decide how which of the principal components you want to use for the display. So this is an example of a parameter tuning interaction. You interact directly with the algorithm, which is an unsupervised machine learning algorithm, and you simply update the data model as you go. Been sick for the last couple of weeks. Anyway, so here's another example. This is some work from years ago that I published called Dysfunction, which is an interactive system for learning a distance function over a set of high-dimensional real-valued data. So you project using multi-dimensional scaling your high-dimensional data into a two-dimensional space, and that means that the distances between the points encode their similarity according to the model. So what that means is if you could have some domain expert in the data look at this and say, this isn't consistent with what I know, they could make adjustments directly manipulating the data points in order to build a model. So this is an example of explicit model steering. They're interacting with the data, but they intend to improve a model with it. They're not just moving points around for the fun of it. And in the back end, we use a semi-supervised metric learner, and we update the data model. And you'll notice there is additionally this point over here where the data model is exportable and readable, which can be very valuable because it means that the machine learning result that comes out of the process can then be interpreted and used to better understand the data going forward. Another example is this Where's Waldo, Finding Waldo paper, where we took a simple game, the Where's Waldo game that many of you have probably seen. You try to find Waldo, this little fellow in the striped shirt here, in a big, carefully drawn scene where he's basically hidden very well. And in fact, if you look on the left there, you'll see there are some distractors meant to make it difficult. It is quite difficult, but it's somehow for children. In any case, what we did here was we recorded every single interaction that people did with the system. So that includes the scroll and pan and all of that, but it also includes just their little ticks with the mouse, every little motion that was done. And those are incidental motions, the kind of flicks of the mouse and so on, and exploratory motions, moving through the image looking for something. We use supervised learning to actually learn models not about the data itself, which was just the image, but instead about the person. So we were able to detect from those interactions, we were able to predict their performance at the task, whether they would do it quickly or slowly, and also to some degree we were able to predict personality traits, which is to say we had them take surveys and then we found with machine learning after a small amount of their interactions we could have predicted it. It exports a model about the users in this case then, because there are decision trees that show how different interaction patterns result in being classified as one group or another. Here's another example. This one I really like because it shows how there are still really fuzzy edges to this. I'm not up here claiming this is perfect and set in stone. Right? So this is ForceSpire. So in this work, Endert et al. Built a system that projected documents into a two-dimensional space. So each dot here is a document, and you can drag and drop different documents around, and that influences their relationship to each other based on the strength of the term relationships. But actually, you can also do things like highlight text. And you could certainly argue that highlighting text is something you might want to do in a document exploration task, regardless of the fact that it helps build the model. So this is a situation where we have either explicit model steering or implicit/indirect model steering, one or the other or both at the same time. But in the end, we use semi-supervised learning to build a data model which is exportable. So I think this one highlights the kind of subtlety of especially that characterization. So the future of the framework here is that I want to expand to a whole bunch of different areas and bring in a lot more examples. If you look in the paper that comes with the proceedings for the workshop, you'll see there's a bunch more than I was able to cover, but there is a tremendous amount more out there. And I'm learning all the time of new communities that have this type of work going on. In particular, there's recommender systems. The machine vision community has started doing work on interactive machine learning, including crowdsourcing. There are the human computation community, i.e. the HCOMP conference, and applied machine learning communities are getting in on this too, including ICHCAI and ICMLA. And I mostly hope that, especially our discussions here, can foster debate about the kind of boundaries and hierarchies inherent in all this type of work that we've been doing. I'd like to highlight the challenges to both the HCI and machine learning communities that come out of looking at the possible space of work. So in HCI, the main thing is that we have to continue to build these tools where we can both capture something that can be used by machine learning and also show the user the effect of machine learning. The main difficulty that rests on the HCI shoulders is that feedback loop has to be closed by an actual human interaction. So both parts of that, where we need to figure out how to capture convenient representations for a person and make them work for machine learning, and the flip side, where we have to make sure that the result of the model is not lost. Those are the most important challenges. And then for the machine learning community, it's not necessarily critical that every algorithm that gets used report an instantaneous result, but if we're having a person in this loop, we need to make sure that we're not interrupting their experience to wait for a machine learner to do its thing. So there are these challenges to build machine learning algorithms or adapt machine learning algorithms so that they can be done quickly in the back end and so that they can support incremental input so that you don't have to rebuild the whole thing necessarily just because someone added a little bit more information. And finally, I like to advocate for comprehensible models, which is the burgeoning field in machine learning, looking at the types of machine learning algorithms that build models that a human can understand after it's completed. I think the best work in this field is going to come from collaboration and getting people to talk across these boundaries and build systems that are actually effective at solving problems. I think we need some real victories where we can show, like in the chess example, an honest-to-goodness concrete example that human plus machine beat out everything else. And with that, thanks very much.